Hello everyone. Thanks to everyone for watching this video. My name is Qida. I am an architect and engineer. Today's video is titled Normal and Shear Stresses, and it is going to introduce the normal stress and shear stress. I am going to give you an overview of what I am covering today's video. First of all, it is a bit of background to the topic, and then focus on the normal and shear stress and strain before wrapping up with conclusions. The strength of a material, whatever its nature, is defined by the internal stresses or intensities of force in the material. We will explore a loaded bar. Here we have a solid metal bar that is loaded by two equal but opposite forces. In this case, the stress is tensile because the forces are stretching the bar. If the forces were trying to shorten the bar, we would have a compressive stress. The sign convention that is normally used is that tensile stresses are positive values. If we fix our bar at one end and apply a force to the other end, the force will cause the bar to deform. The other type of stress is shear stress. If our bar isn't loaded along its axis, but instead perpendicular to its axis, like this, the internal forces that develop within it are oriented parallel to the bar's cross-section. These internal forces are called shear forces. Shear loading is common in bolts, for example. We can understand shear stresses by looking at the stresses acting on a small element within our bar. We have a shear stress on one face of the element, but the element needs to be in equilibrium, so we must also have shear stress on the opposite face in the opposite direction. And to maintain rotational equilibrium, we must also have two-dimensional shear stresses, as shown here. These four stresses all have a magnitude equal to 2, and define the shear stresses acting at a single location. Shear stresses cause a rectangular object to deform like this. Now we will learn the details of the normal and shear stresses. Consider a cylindrical bar AB, which has a uniform cross-section throughout its length. Suppose that at each end of the bar, the cross-section is divided into small elements of equal area. The cross-sections are taken normal to the longitudinal axis of the bar. To each of these elemental areas in equal tensile load is applied normal to the cross-section and parallel to the longitudinal axis of the bar. The bar is then uniformly stressed in tension. Suppose the total load on the end cross-sections is P. If an imaginary break is made perpendicular to the axis of the bar at the section C, then equal forces P are required at the section C to maintain equilibrium of the lengths AC and CB. This intensity of force is known as stress. The tensile stress sigma at any normal cross-section of the bar is P over A, where A is the area of the cross-section. At a given load, the ratio of the extension of any length to that length is constant. This ratio is known as the tensile strain. Suppose the initial unstrained length of the bar is L, and the delta L is the extension due to strain. The tensile strain epsilon is delta L over L. If the material is stressed in the linear elastic range, then the material obeys Hooke's law. The ratio of stress to strain is known as Young's modulus and is denoted by E. The value of E defines the constant in the linear relation between stress and strain in the elastic range of the material. We have E equal to sigma over epsilon. The extension delta L of the length L is expressed as P times L over E times A. Suppose the area of the bar cross-section and the length of the bar are unit. Then the bar has unit volume, and the normal forces on the cross-sections are sigma, if at a tensile force sigma. the bar is stretched a small additional amount d epsilon, then the strain energy on the bar is approximately sigma times d epsilon. The strain energy is directly recoverable on removal of the load, and the strain energy U is the integration from 0 to epsilon, then obtain half of E times epsilon squared. We also know epsilon is equal to sigma over E, then substitute it into the strain energy equation. The strain energy can be rewritten as sigma squared over 2 times E. Now we made a study of normal stresses. Next, we will learn another type of stress which plays a vital role in the behavior of materials. Consider two flat plates held together by a single rivet and carrying a tensile force F. We imagine the rivet divided into two portions by the plane AB. Then the upper half of the rivet is tending to slide over the lower half, and the shear stress is set up in the plane AB. Shear stress on any surface is defined as the intensity of shear force tangential to the surface. The average shear stress tau over the section AB is F over A. Let us now consider the equilibrium of an elementary block. Let tau xy be the shear stress on the horizontal faces of the element, and the tau yx the complementary shear stress on vertical faces of the element. Suppose A is the length of the element, B is height, and that it has unit thickness. The total shear force on the upper and lower faces is A times tau xy. The total shear force on the end faces is B times tau yx. For rotational equilibrium of the element, we then have A times tau xy times B equal to B times tau yx times A. Then we obtain tau xy equal to tau yx. We see that whenever there is a shear stress over a plane passing through a given line, there must be an equal complementary shear stress on a plane perpendicular to the given plane and passing through the given plane. The directions of the two shear stresses must be either both towards or both away from the line of intersection of the two planes in which they act. Shear stress in a material give rise to shear strains. Consider a rectangular block of material again, subject to shear stress tau in one plane. The shear stresses distort the rectangular face of the block into a parallelogram. If the right angles at the corners of the face change by amount gamma, then gamma is the shear stress. The angle gamma is measured in radians and is no-dimensional. For many materials, shear strain is linearly proportional to shear stress within certain limits. This linear dependence is similar to the case of normal stress. The shear strain tau is equal to G times gamma, where G is the shear modulus or modulus of rigidity. In shearing the rectangular prism, the forces acting on the upper and lower faces undergo displacements. Therefore, work is done during these displacements. If the strains are kept within the elastic limit, the work done is recoverable and is stored in the form of strain energy. Suppose all edges of the prism are unit length, then the prism has unit volume, and the shear forces on the shear faces are tau. Now suppose tau is increased by a small amount, causing a small increment of shear strain d gamma. The work done on the prism during this small change is tau times d gamma, as the force tau moves through a distance d gamma. Therefore, the strain energy is expressed as this equation. The strain energy also can be rewritten as tau squared over 2 times g. Now we can make an example to show the application of the normal and shear stresses. This slide shows bolted joints. Bolted joints are widely used in structural steelwork. This picture shows joints between two plates of material. Suppose the plates are each of thickness T and that they are connected together with a single line of bolts, giving a total overlap of breadth 2A. Suppose also that the bolts are each of diameter d, and that their centers are a distance b apart along the line of bolts. The line of bolts is a distance a from the edge of each plate. It is assumed that a bolt fills a hole, so that the holes in the plates are also of diameter d. We consider 4 possible simple modes of failure when each plate carries a tensile load of P per unit width of plate. First, the bolts may fail by shearing. If T1 is the maximum shear stress, the bolts will withstand. The total shear force required to shear a bolt is T1 times the area of the circular hole. The load carried by a single bolt is P times B, so that a failure of this type occurs when P times B equal to the shear force of the bolt. Next, the bearing pressure between the bolts and the plates may become excessive. The total bearing load taken by a bolt is P times B. If Pb is the pressure at which either the bolt or the hole fails in bearing, a failure of this type occurs when P times B equal to Pb times T times D. Next, tensile failures may occur in the plates. The most heavily stressed areas of the plates are B minus D in a bracket times T. If the material of the plate has an ultimate tensile stress of sigma ultimate, then a tensile failure occurs when P times B equal to sigma ultimate times a bracket of B minus D. The last is that shear of the plates may occur on planes. The shear area is 2 times A times T. If T2 is the maximum shear stress of the material of the plates, this mode of failure occurs when P times B equal to T2 times 2 times A times T. From conclusions, what we learned? Normal stress is a stress that occurs when a member is loaded by an axial force. Shear stress is a component of stress coplanar with a material cross-section. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.